Hi everyone, I'm going to go ahead and solve two examples of vertical spring word problem with you. So if you look at this one, it says that a trampoline, it lies in the unstretched position at ground level and a 4.2 kilogram mass. So you have a mass that's 4.2 kilograms. Is initially at 5.59 meters above the trampoline. So the initial height is 0.59 meters. And the mass is released from rest, so its initial velocity is going to be 0. So the initial velocity is going to be 0. And the mass as it lands on a trampoline, and the mass in the trampoline, the mass causes the trampoline to get compressed. So there's a compression distance, which I'm calling xc, which is 0.19 meters. So given that information, what is the spring constant? All right, so let's just try to reinterpret what we have here. So the picture looks like this, is that there's, let's assume that this is ground level, and the mass starts, so ground level at the origin here, the mass starts off up here with the initial height y initial, and it's at rest with the velocity v initial. So that's from the mass's perspective, and from the spring, we're going to need another coordinate system. So I'm going to call this the origin for the spring position. And the spring starts here at the unstretched position. So that means that the initial position of the spring, x spring initial, is going to be 0, because it's at the equilibrium position. And now afterwards, the mass lands on the spring, and it compresses the spring downwards. So going back to the coordinate system for the mass, for the y-axis. Now, this is still the ground level. Now the mass lands on a spring, and it compresses the spring down to a distance of y final. So we'll just leave it as y final for now. But notice that this is the origin here, and this is below the y, the origin, so I'm going to make this a negative here. And similarly, so this is the final state for the spring in a spring coordinate system. So the spring is drawn here, but I'm going to redraw it here just from the spring's perspective. And from the springs in the spring coordinate system, the spring is compressed by the distance x compression, which we have here, the 0.19. And so here we're going to also define that to be negative. So the thing to notice is that the distance that the mass is below the origin is the same as the spring compression. So I'll just say, looking at the absolute values, the spring compression is going to be the same as the final height of the mass. And once the mass, once the spring is completely compressed, it's going to come to rest. So the final velocity is also going to equal 0. So I'll go ahead and put that constant here also. So the final is also going to equal 0. All right, so now the general equation for conservation of energy is work done by an external force plus work done by friction equals the change in kinetic energy, so 1/2 m v final squared minus v initial squared, plus the change in potential energy, which is going to be mass gravity, y final minus y initial, and plus the spring potential energy, which is going to be 1/2 the stiffness of the spring multiplied by the stretch of the spring, which is going to be final position of the spring minus equilibrium position squared, and then minus the initial position of the spring minus the equilibrium position of the spring squared. So that's the general equation, but there's a lot that we can simplify here. First of all, there's no external force, so that term is going to disappear. And also there's no friction, so that term is going to disappear. And final velocity is 0, so this term goes away. And initial velocity is 0, so this term goes away. So all that's left from this equation is 0 equals mass gravity final height minus initial height plus 1/2 the stiffness of the spring. And we can simplify this some more here. Let's see. Initial position of the spring is 0 and it's at equilibrium, so x equilibrium is also 0. We're going to find it to be 0. So here, equilibrium is going to disappear, and also initial position of the spring is going to disappear. So then this equation is going to be, what you're going to be left with is 1/2 k multiplied by x spring final squared. And here also we can make further simplifications. So from this picture, the final position of the spring is below the origin, so that's negative, and the spring position is also below the equilibrium, so that's negative, and they're both the same value. So I'm going to just simplify that. So x spring final is going to be the same as y final. And one more thing, y final, I'm going to make that a negative. Because, well, let's just do it one piece at a time. So the final position of the spring is below the horizontal. So that means that I'm going to replace this with a negative. So it should be a negative y final. And here, for this term here, this final position of the spring is the same as the final height of the ball. And technically they're both negative, but because of the power of 2, I'm going to ignore the negative. So then this equation will be simplified further to 0 equals mass gravity multiplied by negative y final minus y initial, and then plus 1/2 k y final squared. And doing the algebra, taking out the common negative factor here and moving things around, this will become 1/2 k y final squared equals mass gravity y final plus y initial. And we want to get the k by itself, so move these other terms around, and you'll get that the stiffness of the spring is going to equal mass gravity multiplied by y final plus y initial, and multiplied by 2 times the final position of the spring squared. And plugging in here, 2, mass of the object is 4.2, gravity is 9.81, final height of the spring is 1.9 or 0.19, initial position of the spring is the 0.59, and divided by the final position of the spring, which is again 0.19 squared. And calculating that, get that the spring constant equals 1.8 times 10 to the 3 Newton meters.